Houston, contact with a test 1.
Hello, it's Scott Manley here. A couple of days ago, I sat down for a video chat with the principal investigator behind one of my favourite space missions right now. Today, we are with Dante Lauretta, who's a principal investigator for the OSIRIS REx mission. That's the space mission out next to the asteroid Bennu. Hello, Dante, how are you?
Doing great, Scott.
So, I guess you're here to give us all the lowdown and all the details that I can never get entirely on my own, right?
Yeah, this is an exciting time for the OSIRIS REx mission. We're NASA's asteroid sample return, and we have been mapping asteroid Bennu for well over a year now. And we made a down select to our primary site, which we call the Nightingale, and we have a backup site called the Osprey. And we are doing a series of low altitude reconnaissance passes over those sites, getting final confirmation of what the surface looks like, and really getting ready to go get that sample in August.
So, how do you actually navigate near the asteroid? Like, is there a coordinate system that you guys have agreed upon? What instruments are you using, etc., etc.?
Yeah, that's a great question, because accurate navigation in microgravity is the key challenge of this program. So asteroid Bennu is about 500 meters in diameter, so it's like a small mountain floating in outer space. And as a result, its gravitational field is incredibly small. We measure it in micro-Gs, where 1 G is the average acceleration at the surface of the Earth, and a micro-G would be 1/1,000,000th of that acceleration. And so Bennu is around 2 to 8 micro-Gs, depending on where you are on the surface. So the spacecraft is pushed around quite a bit by other forces, like solar wind, heat coming off the asteroid, any kind of outgassing from the spacecraft. You can imagine it just being buffeted around because the gravity is so low from Bennu. So we use a technique called landmark tracking optical navigation. We have a coordinate system of the asteroid. We have very accurately registered specific features, craters, and boulders on the surface of the asteroid. And then every day, every couple of hours, we take images of the surface, just pointing the spacecraft down. And then we register those landmarks, and on the ground, we reconstruct where the spacecraft was when it took those images. And then it makes a prediction up to 7 days into the future about where the spacecraft's going to be. And because of the nature of those small forces, we're constantly updating that prediction. And if we need to make very precise observations of a region on the surface, like where we want to get our sample from, then we have to update that prediction within 24 hours of making the observations.
So, like, how tightly bound is OSIRIS REx in its current orbit? How fast is it moving, and how long would it stay in that orbit if you turned off its navigation?
Yeah, amazingly, the orbit that we've found is incredibly stable, and we probed around for different parameters to find out this, what we call a frozen orbit. So it basically stabilizes all those forces. We've measured them down to 13 decimal places, literally significant figures down to 13 digits, which means we can make very accurate predictions about how those forces are going to affect the spacecraft. And so we would stay there for months if we lost contact with the vehicle, as an example. And it's within about 1 kilometer from the center of mass of the asteroid.
How long does it? What's the period at 1 kilometer out then?
So we're moving at about 10 centimeters per second. It takes us a little over 20 hours to make a single orbit around the asteroid.
And Bennu's rotation rate then is
4.3 hours.
4.3. So yeah,
Bennu's
so this is
spinning 5-6 times underneath us as we orbit around the asteroid.
Right. So yeah, that's cool. And so you're basically in this frozen orbit. You found this by essentially flying many orbits, I guess, to measure the exact mass distribution inside the asteroid.
Yeah, the mass distribution and all those small forces. So we have a very detailed model of the spacecraft and how it interacts with the solar radiation pressure and the heat coming off the spacecraft and the heat coming off the asteroid. All of those forces go into our orbital equation. It's not just Kepler's law. There's a lot more to it when you're trying to do something this precise around an asteroid like Bennu.
So give us an idea of the order of the forces then. You've got the gravity of the asteroid, you've got solar radiation, and you've got the thermal radiation re-radiating from the asteroid. Is there anything else?
Any kind of outgassing from the spacecraft, which tends to be a stochastic event, meaning that it happens suddenly. If a new surface gets illuminated, then a patch of ice that might have condensed on the spacecraft sublimates and it pushes us around. So those we have to just watch out for. And we've really done a campaign to kind of get all those little nooks and crannies illuminated to minimize any event like that. So we only worry about that if we're going into a new attitude, a special observation that needs to take place, like the sample acquisition event. That's a whole series of new attitudes for us to do that, to make sure those forces don't come into play. But they can be substantial. They can be more than solar radiation pressure when they occur.
So where's the ice condensing from? Is it propellant or is it coming out of Bennu?
We're pretty sure we picked up a bunch of water in Florida when we were getting ready to launch. Okay. And there's just a lot of absorptive surfaces, especially the sample return capsule being a heat shield that's very low density and low thermal conductivity. So it sucked up water, and then that water kind of came out in the vacuum of space and then moved to all the cold traps on the spacecraft.
Oh, wow. So that's so you're going to have to do something like a barbecue roll prior to
That's exactly what we did. Yeah, we've done that, and we did that repeatedly, and we could see the forces dropping off every time we exposed those surfaces to solar radiation until they got to the point where now if the known areas of outgassing get illuminated, it's a force that we can deal with and won't knock us out of orbit. When we first saw it happening, it was a real surprise. And we said, geez, if this happened in orbit, it would literally push us away from the asteroid. It's that strong.
So you found this before you got into orbit, right?
Yeah, we noticed this during outbound cruise when we were heading from the Earth to the asteroid, and we were checking out some precision thrusting, and these small forces started showing up, and we had to chase them all down.
Yeah, and we've also, by having the spacecraft really close to Bennu, we've now obviously got its orbit really well determined compared to any other asteroid, right?
That's right.
So we'll know where it is for a long time to come.
And that's really important because it is a potential Earth impactor, and that's one of the key objectives of OSIRIS REx is to study the Yarkovsky effect, which is similar to what we've been discussing because Bennu is relatively small. When it heats up and then emits that energy as infrared radiation into space, that thrust changes the orbit of the asteroid. That's called the Yarkovsky effect. And so one of our mission objectives is to measure that and fold that into the orbital solution for the asteroid and accurately predict its future path, especially the likelihood that it's going to impact the Earth.
Yeah, and the Yarkovsky effect can actually be bigger than that of solar radiation because it tends to get given off at the terminators, right? Therefore, it's prograde or retrograde.
Yeah, preferentially the afternoon because that's where you've just gone through noon, you got really hot, and then you're moving into shadow and you're radiating. So and you mentioned prograde versus retrograde, that's really important. Bennu's a retrograde rotator, which means its afternoon is in the direction of its orbital motion. So it's like putting on the brakes and slowing it down because you're pushing energy opposite the direction you're traveling. So that results in the semi-major axis of the orbit decreasing. If it was a prograde rotator, it would be accelerating and its orbit would be expanding.
Yeah, this is also obviously stuff that a lot of my audience have learned from playing video games. And we should probably mention that you like to play games and you like to design games.
Absolutely. Yeah, I'm a board game designer, and I use science-themed board games to get people excited about space exploration and to learn some cool science concepts.
So you've got a Kickstarter campaign right now for the sort of upgrade 2.0, Xtronaut 2.0?
Correct, yeah. We launched our first game on Kickstarter in 2015 called Xtronaut, and it was capturing my experience getting ready to launch OSIRIS REx on its journey to Bennu. And so being the first game, there's always things you wish you could have gone back and done differently. We also have over 12,000 copies that we've sold, so we get a lot of feedback from our players who are very avid fans, and they get in touch with us quite a bit about what they would like to see in the game. So we've listened to them. We've incorporated our own experience. The biggest upgrade is it now covers 2 to 6 players. The previous game was 2 to 4 players, so we expanded the size of the game. We added a lot more of the action cards, which are how the players interact with each other. It's got a bit of take that action and can be quite cutthroat at times.
Oh, yes.
Which does mimic the real life experience of trying to win a NASA mission and get it to the launch pad. And overall improvements in the flow of cards, how you draw cards, how you discard cards, and how you gain action cards.
I played this a while back. Certainly, it was only the 1.0 version. I don't have my copy anymore because I think I gave it to somebody as an emergency present, but they liked it a whole lot.
Well, now's the perfect time to upgrade to 2.0.
It is a perfect time. There was some other games that you've made as well. There was the Stars one, right?
Yeah, we did. Let's see. I've got them here. If we want to take a look, I got the Constellations game.
Oh, right. Yeah.
Is about the night sky. This is a more Zen-like game. If you like calm and peaceful gameplay that's somewhat cooperative. I mean, you're trying to win. Constellations is for you. And then I think the most serious game that we've done is called Downlink, the game of planetary discovery. This is more for your hardcore gamer audience. It's going to take you a couple hours to get through that. And of course, Xtronaut 2.0 is the one that's on Kickstarter right now.
So where do these fit compared to, say, High Frontier, which is the legendary complicated space exploration game?
Yeah, so Xtronaut, we say, is for players 8 and up. So you can play with your kids. Gifted younger kids certainly can play it as well. Downlink, we say, is 10 and up, so it's not quite at the High Frontier level, which would be a 14 and up kind of game.
I have trouble with High Frontier.
Yeah, High Frontier is a serious game, right, where you're going to spend many hours of gameplay. Downlink is a step towards that from Xtronaut, but not quite at that level.
Okay. So let's go back to OSIRIS REx then. We're getting ready for the sampling. I'm actually really curious, as the principal investigator, how you and your team decided to go for the current sampling mechanism over other candidates.
Well, that's a long and storied history. So I've been working on this program over 16 years now, and that was a decision that was made almost right at the beginning in 2004. And it really was a trade. We needed to come up with a system to get a lot of sample. That was one of the things I said right away. We're not interested in a few grains of dust. We want big chunks of rock off the surface of this asteroid, a couple of centimeters or more if we can get it. And we want tens of grams, if not kilograms of material. So we needed something that was going to get us a lot of sample. We actually traded landing on the surface and doing extended surface operations versus the very quick touch and go. And especially in 2004, we hadn't even seen images from Itokawa, which was the Japanese target for their Hayabusa mission. We didn't really know what we were up against, but we knew the environment was going to be very low gravity and probably a very loose surface. So trying to design a spacecraft that could stabilize on something like that, we didn't have enough information to have any confidence. We saw what happened with Rosetta when they tried to do that, right? They had a lander, they had harpoons, they couldn't stick the landing, and they bounced around on the surface and ended up in a crevice. So we said we got to go with the touch and go. So we needed something that would get a lot of material in about 5 seconds of contact with the asteroid surface. We also knew that our prime mission was to bring back organic material. So it had to be a system that you could clean really well, because we didn't want to contaminate it with solvents or biologic entities from the Earth. And that meant minimizing moving parts. So all of a sudden, drills and claws, things that had motors, that became really challenging because you just can't bake those out at the high temperatures you need to sterilize them. So it had to be kind of passive, had to collect tens of grams or more of sample in 5 seconds, and it had to be cleaned like autoclave clean. So that led us to the gas stimulation. We're like, we can build a filter. It's basically out of aluminum and stainless steel that you can clean very easily. And then the force is coming from gas, which you can also purify and has no moving parts other than the valve that opens it up, and that can be way up on the robotic arm. So all of those trades came down on what we call gas stimulation sampling and ultimately our TAGSAM device.
And I'm curious how much lab testing this got. Like, did you test it like in a vacuum chamber in 0G or on a plane, or? Yes,
sort of. So the goal that we never could achieve was true vacuum and true microgravity. Basically, an exact simulation of the conditions on Bennu. That's really, really hard to do. So we did fly on NASA's C-9B spacecraft, which was called the Vomit Comet. It's been decommissioned, unfortunately. They don't fly it anymore. And so our first request to them was 0G, right? We really want no gravitational acceleration. But you're on an airplane, so there's noise. So they target 0G, but you have some positive G and you have some negative G. And the negative was invalidating the test because that was causing an upward acceleration, and it was pushing material into the sample head, and therefore we weren't actually testing the collection of the device itself. So I said all those results are useless. We throw them away. We got to redesign the experiment. So then we went to the pilots, and they really took this challenge well. And we said, we need the slowest positive acceleration with guaranteed no negative acceleration. And that ended up in the milli-g range. So that's a thousandth of the acceleration at the Earth. You know, we were flying around and having fun and floating in microgravity, but it's still 1,000 times more acceleration than exists at the surface of Bennu. So it turned out it's impossible on Earth to reproduce the microgravity environment without introducing negative accelerations, and we settled for the milli-g environment. And then we wanted a vacuum, but flying a vacuum chamber on that aircraft was cost prohibitive. And there's a lot of safety requirements about doing that. So what we ended up doing was venting out the side of the aircraft. We were way up in the atmosphere, so we were in the millibar range of pressures, but still not vacuum. So we did a lot of testing on that airplane, dozens and dozens of tests over a wide variety of parameters to optimize the design. And then we tested in a true vacuum chamber on Earth, but still under Earth acceleration. The good news is what we showed is kind of what you'd expect, that as you go to lower accelerations, the efficiency gets better because you don't have the force of gravity holding the regolith down. So we said, well, if we just test in vacuum, which turns out to have a large effect because we're using gas stimulation, an atmosphere really changes the flow dynamics. Anything that we collect in 1G is a worst case, and we should do better than that at Bennu. And so we kind of just settled on for the extensive test program that would mostly be done in a vacuum chamber.
So that's better than what you expected at Bennu, but as I understand it, you've looked at the surface of Bennu and it's a little more rough than you'd expected.
Yeah, we really got surprised by Bennu. Basically, we relied on a couple pieces of astronomical data. The first and the most convincing one was the thermal inertia. We talked about Yarkovsky effect and emission of thermal radiation. Well, you can measure how fast an asteroid surface heats up and how fast it cools down, and we call that its thermal inertia, its resistance to change in temperature. And Bennu has a very low thermal inertia. It heats up quickly and cools off very quickly. And that looks like fine-grained material, like sandy beach, and we use that term a lot in development. This is going to be a sandy beach because it's heating up and cooling off very, very quickly, where boulders tend to heat up very slowly and cool off very slowly, and they have a very high thermal inertia. So we had measured that using the Spitzer Space Telescope, and it looked like fine-grained material, at least centimeter-sized particles and smaller. And then we also used the Arecibo radar system, and we sent polarized radio waves, and we looked at the polarization return, and that tells you how rough the surface is at radar wavelength scales. For Arecibo's 12.5 centimeters, and it looked really smooth at the 12.5 centimeter scale in radar. So it's like, it's a smooth surface. We repeated that experiment with Goldstone, which gets down to 3.5 centimeter wavelength. It still looked smooth. And so it looks radar smooth, and it's got a really low thermal inertia. It should be covered in fine particles. Not the case. We get to Bennu. We see those first images in December of 2018, and it is rugged and rocky with giant boulders everywhere. Huge boulders, some of them up to 100 meters across.
I heard the big boulder's now got a name. Yeah,
the big boulder, which is the darkest object on the surface, is called the Rock. And that's the ROC. It's the rock from Sinbad mythology, right? Everything on Bennu is named after mythological birds or bird-like kinds of creatures. So yeah, we got the Rock. We got another giant one called the Gargoyle, which stands 15 meters tall. And there's millions of rocks, and we've counted millions of rocks. We actually crowdsourced our rock counting out through CosmoQuest, and we had tens of thousands of people help us count these rocks. And we're looking at new ways to crowdsource some data analysis. We have some new ideas that are in formulation right now. So it's a huge puzzle. Bennu does have that low thermal inertia. We verified that. We have a thermal emission spectrometer on the spacecraft. Bennu is heating up and cooling off very quickly, but it's the boulders that are doing it. So we're dealing with a material that we're not familiar with. And it must be like styrofoam or something like that.
Highly porous boulders that are glued together with, I don't know.
Yeah, dust bunny kind of thing.
If only you could bring a boulder back and find out.
Well, we're going to bring chunks of it. So the good news is there's a few small patches of sampleable material on this asteroid. And one of them, the best one, is the Nightingale site. And we just got images down at the end of last week we flew at 245 meters over the surface, and we're imaging with a pixel scale of 3.8 millimeters. So it really is microscopic imaging of the surface. And we see lots of rocks that are a couple centimeter size right in the area that we're targeting for sampling. So we're going to get a good sample off this asteroid. We just had to really tighten up our navigation accuracy to make that happen.
Yeah, so you're gonna now hold on, the navigation for the actual pickup, how is that gonna work?
That's all autonomous on board the spacecraft, and that was where the big upgrade came into play to deal with these really tight sample sites. Before, we were using a laser system called a LiDAR, which is like a radar but using a laser beam instead to give you altitude information. And because we thought we were going to have big sandy areas, we only needed to really know our approach to the surface. And we didn't really care about what we call cross-track uncertainties. But as we looked and said, with the LiDAR, you can hit a spot within 25 meters of where you pick. But we need to get within 5 meters or smaller on this asteroid. So we had to scrap the LiDAR approach, and we used the camera systems, and we put an onboard catalog of all these features. And now the spacecraft has the ability to take a picture, refer to the catalog, and say, do I recognize any of these features, and then triangulate on those, and it can do a complete solution, not only where it is in space, but what its velocity is. So now it has really great knowledge, and it's going to use that knowledge to update the maneuvers, the final 2 maneuvers for the descent down to the surface to get a guidance accuracy that we require.
And if it doesn't detect, or if it doesn't figure it out, it'll probably have a back off, contingency.
Exactly. Yeah, it can wave off. It'll get all the way down to 5 meters from contact, and that's the last chance it has to wave off. So we have also on board a hazard map, because even though these sites look sampleable, there's some big rocks around it that we don't want to contact, and they're low probability events, but still possible. So if the spacecraft predicts it's going to hit one of the hazardous boulders, it'll just say, wave it off, fire thrusters. We're in microgravity. It's not a huge thrust. And then we just reinsert into orbit and try again.
And that's going to take place later this year. So what will the light time delay be at that point?
Yeah, no, we're going to be at least 15-minute one-way light time.
Oh, so it's like far side of the sun.
Yeah, exactly.
Wow.
Yep. Yeah, so it's all happening in the past, right? We'll be getting the telemetry. You got to also remember, we're not on our big antenna, our high-gain antenna. We're on the low-gain. The data during sampling is coming in at 40 bits per second, right? So it's what we call breadcrumbs. I mean, you're just getting a few flags from the spacecraft that tells you certain sequences have kicked off in the software. And we'll also be getting the coordinates of that natural feature tracking system. It'll tell us where it is and what its predicted point of contact is. And so every once in a while we have the breadcrumbs, and we say every once in a while we throw in a crouton, which is a bigger chunk of data about its positional knowledge.
So you won't be getting live imagery until you're going to have to wait until you get a better antenna, or what's the constraint
So we're
there?
going to go in, we're going to make contact, we're going to back away, and then as soon as we stabilize, we're going to point the high gain antenna at the Earth and start streaming the data back.
Great. So how long will that be before we get to see the cool pictures of this?
Good question. The team is working. They have the direction for me to make that as quick as possible, especially, the money shot of contacting the surface. We're saying by the next morning, we should have an image for everybody to take a look at. So we'll be contacting around 2 in the afternoon, Mountain Standard Time. So we're going to give ourselves overnight to get all that data down and get the public what they want to see about how that whole event went.
Okay, so I'll have to get my video ready for that image coming in, right?
Absolutely.
This has been fabulous. I think we can we say we've learned a lot here, right?
Great, absolutely.
Thanks for all the information. We really hope the OSIRIS REx has a fantastic experience with its landing, and watch the surface, and of course fly safe, right?
Thank you.